The Regula Falsi method is a method for locating a zero of a continuous function. So we're still in the same kind of vein of like the bisection method, the Newton method, the secant method, and then now the Regula Falsi method. This should look exactly like the secant method formula to you. The only difference between the Regula Falsi method and the secant method is this. For the Regula Falsi method, it's kind of like the bisection method in a way, where we are going to begin with an interval from A to B, where on one end of the interval, I've got a negative value, and on the other end of the interval, I've got a positive value. And the way I calculate the next iterate is not like the bisection method, though. I'm not just going to take the midpoint between A and B. Instead, I'm going to draw a straight line from B to A. And then this point is going to be the next iterate. And since this point is positive here, then I would move the upper bound down, and this would be the next B. So it's like the secant method because we are calculating a secant line between 2 points on my function, and then we find the zero of the secant line, and that becomes the next iterate. That's exactly what the secant method does. But it's also like the bisection method in that we are only going to ever interpolate between 2 points where the endpoints of my interval are always opposite in sign. One's negative values of the function, one's positive value of the function. So this, in theory, could be better than the bisection method. Because if I had used the bisection method here on this picture, then my next upper bound would be farther away from the true zero than this one is, right? You see how that one step is at least better than the bisection method would be? But hopefully we get closer than the bisection method. And then the other thing you might compare it against is the secant method. Is this better than the secant method? And in a way, kind of, yeah, because the secant method could always diverge to infinity, right? We saw some problems where we started off the secant method and it blew up before it found a zero. The Regula Falsi method is like the bisection method in that it's guaranteed to converge because you're always just going to be trying to narrow down an interval. And so given enough time, it will converge to the zero. It also has the drawback of the bisection method, which is that you've got to start off with this interval. You've got to find an appropriate valid interval to start off with. But that's the whole idea. And that's why the formula looks so much like the secant method formula. Questions? Does that make perfect sense? Okay, let's do an example. So we'll use the method and a calculator to calculate the zero of the following function, arctangent of x, to within 0.1. And we'll use the initial interval from -1 to 20. And so I'll keep track of what iteration we're on. And we'll keep track of the lower bound and the upper bound. And I'm going to try to recall my formula because the new iterate is going to be a minus f of b we'll say divided by m, where m is f of b minus f of a divided by b minus a. It is upside down, because dividing is the same as multiplying by the reciprocal. And by the way, you'll notice that I wrote b minus a, and up here in the formula that I typed out a minus b. But if I reverse the order of subtraction in the numerator and denominator, then it's fine. It's the same thing still. It's like multiplying the top and bottom by -1 when I reverse that order of subtraction. You just got to make sure it's in the same order. And hopefully that's it. I'm trying to think if there's anything I'm forgetting. But I think that's the whole deal. We'll see if it works. If it doesn't work, then I know I did something wrong. So we'll find f of a, f of b, and then m, and then f of b divided by m, and then we should be able to calculate the next iterate after that. Okay, so for iteration number 1, a is -1, b is 20. F of -1 is arctangent of -1. And you know what? I'm just going to do this on Excel because I don't want to waste your class time while I fumble around with calculators. So let me just recreate this table on Excel, and that way it's going to go faster after we get this thing set up. But you get the idea of what you might do on a test. And -1 to 20. And so my function is the arctangent. M is like f of a minus f of b divided by a minus b. F of b divided by m is this, and so the new one is going to be a minus f of b divided by m. And the other thing I need to know is what is my function evaluated at this new iterate? Because I really need to know if that's positive or negative so I know whether I'm going to replace a with it or replace b with it. And if this is negative, then I'm going to use it to replace a. Okay, I knew I had a bad feeling about this. There's some kind of issue with the formula I came up with. Do you see how I know that there's an issue? Since this function has a negative value, it should really be replacing a, because the function has a negative value at a. So it should be replacing the -1. But the problem is that I calculated something outside of my interval. I should always get something in between a and b. I should always get something between -1 and 20. And so -15 isn't it. So let's think about this for a minute. Let me draw a picture, and maybe we can figure out what was wrong with my formula. Right? So here is a, here is b, and my function has some negative value here and some positive value here. And I want to know the secant line, right? And the secant line has a slope, which is this. We weren't wrong about the slope part. But then if I need the formula for the secant line, I'd have to do y minus f of a equals m times x minus a. And then I'm trying to find the place where y is equal to 0. So then I could write negative f of a equals m times x minus a times m. Or I should just divide by m, rather, because I'm trying to solve for x. I'm not trying to solve for the function. So divide both sides by m, and then add a to both sides. So x should be equal to a minus, there it is. I see the issue. I'll have to try to remember to go back and fix this in my notes. But the problem, and remember to fix this in your notes at least, is that that should be an A. Oops, not a B. There's an equivalent formula that we could use where you could make that a B and make that a B. That works too, but this either needs to both be A or both be B. Okay, so we fixed it. And now I'll go fix it on my spreadsheet. Okay. This looks good to me because my new iterate is in the right interval between -1 and 20. Yeah, 6.15. And the function value there is positive, and so that means, should I replace A or B? B. Yeah, because f of B is positive, and so that means on my next iteration, A gets to remain the same, B is now my new iterate, and then I'm going to copy down all these other formulas. So on the second iteration, only have the interval from -1 to 6. And my new iterate from finding the 0 of that secant line is 1.55, 1.56. The function there is positive, so should I replace A or B? If the function is positive. B. Yeah, I need to replace B again. So now for my third iteration, A remains the same. B gets replaced by the new iterate. And then I keep the same functions. So in my third iteration, my new iterate that I get is 0.125. The function is positive, so I replace B again. And A remains the same. Now my interval is shrinking, right? It's getting pretty small between -1 and 0.125. My new iterate is -0.029, and my function is negative here. So if my function is negative, should I replace A or B? A. So now let's replace A for iteration 5, and B remains the same. Now my new iterate is positive and the function is positive there. And since the function is positive, I replace the B. A remains the same. Now the function is negative, and if the function is negative, then A gets replaced and B remains the same. And now I'm getting pretty close to 0. By the way, the 0 of arctangent is 0, and so I'm getting pretty close. I wonder to myself if this would be any better than just using the bisection method. Because it's really not as good as you would think. Especially in the beginning, it looks like it's a lot better than the bisection method because like we're shrinking the interval from 21 down to 7 instead of just 21 down to like 10.5. And then shrinking it down from 7 to 2.5, which is better than half. And then you shrink it from 2.5 down to 1, which is still a little bit better than half. But really the answer is sometimes this outperforms the bisection method, and sometimes it doesn't. There's really not one that's strictly better than the other. The longer explanation, if you're like a real nerd, is that if the concavity remains the same over your starting interval, then I think the bisection method is better, because if the concavity remains the same, do you know what concavity means? Concavity is the sign, the plus or minus sign on the second derivative of your function. So if it looks like a rainbow, it's concave down, and if it looks like a smiley face, it's concave up. And if the concavity is constant, like it's always positive or it's always negative across an interval, bisection method is better. If the concavity changes, especially if the concavity changes near your 0, then the Regula Falsi method is better. I'm not going to expect you to know that, but it did really well this time because arctangent switches concavity at x equals 0. It switches concavity exactly at the 0 you're supposed to find. And so it actually does really well for arctangent because the concavity switches. It has an inflection point. That's the fancy word I tell the Calculus 1 students. If the second derivative switches from positive to negative or negative to positive, we say it's an inflection point. So if you have an inflection point near your 0, the Regula Falsi method does better. If you don't, then the bisection method might do better. Okay. Implement the Regula Falsi method in Python using a for loop, then use this code to find a 0 of this function with 10 iterations. So let's do this in Python. We'll see what it might look like. I'm probably going to try to start with my secant method code in Python and then just tweak the secant method to make it work, since it's so similar in formula. Or maybe I should start with the bisection method code and tweak it. I guess it depends on what I can find first. Newton's method is like the easiest thing for me to remember how to code because you don't have to do any if statements, right? It's just a loop with one function. But these more sophisticated ones, like Regula Falsi, take a little bit more effort. So I'm going to open up my bisection method, and then I'm going to save a copy to be my Regula Falsi. And the function that I'm interested in is 2x cubed minus 4x squared . 2x cubed minus 4x squared plus 3x and my starting a is going to be -1, b is +1. So this time I don't care what the midpoint is. My new iterate is just going to be what I get from that crazy formula, which is like a minus f of a divided by m, and m was f of a minus f of b divided by a minus b. And other than that, it's the same as the bisection method. It's just the bisection method where we choose a different way to pick a midpoint. So let me run it and see if it works. So it did 8 iterations. Each time I want it to print and tell me what the x new is. Try it again. There we go. So not so great. Let me see if the bisection method gets closer in 8 iterations. Print midpoint. Oh, well, it's a different function. Let me get the right function. Boop. Boop. Okay, now we try the bisection method. And bisection method seems to be converging to 2. Oh, because I used the wrong interval. Okay, let me fix the interval now. And now, what happens? Oh, because the 0 is at 0. Okay, so I can't use exactly that. I've got to choose something else. Okay, there you go. So this function does have a 0 at x equals 0. And the Regula Falsi method, when I click run, it doesn't do a very good job, right? Like after 8 iterations, we only narrowed it down to like 0.05. When I run the bisection method on the same thing, I get, after 8 iterations, 0.001. So that's just to show you that Regula Falsi might be more sophisticated. It might look like it's a smarter idea. Sometimes it's faster and sometimes it's actually slower than the bisection method. This seems to be a particularly slow example of doing Regula Falsi because notice that if I were to also print what the lower bound is every time, the lower bound doesn't change. When you get into these regimes where you have a constant plus or minus sign on your second derivative on the concavity, then one side of the Regula Falsi interval will remain fixed and only the right side will change and get closer and closer. Or maybe the right side remains fixed, but the left side will change. And with the bisection method, imagine this, the bisection method, the interval always gets cut in half every single iteration. You're guaranteed to cut the interval in half with every iteration. So the limit of the width of the interval as your iterations approach infinity is 0. That's important enough I should write it down. For the bisection method, with k iterations, the limit as k approaches infinity of the width of the interval is 0. But this is not true for the Regula Falsi method. Because if you get into a regime that has like a strict plus or minus concavity, right, over an interval, then only one side of the interval is going to move. The right side's going to move left or the left side's going to move right. But it's not going to move until the interval shrinks to 0. It's only going to move up to the point where you're getting kind of close to the 0 you're trying to find. It's not going to move past it. And so you have this interval that will never shrink to 0 the way that the bisection method does. And again, I'm not trying to throw too much shade at the Regula Falsi method because sometimes it is faster, but I just want you to know that it's not necessarily always faster than bisection method. What if I want to use a while loop and I want this function to have 6 significant figures of accuracy? Then we can try to implement that. We can try to do a while loop. I would say while my estimated relative error is greater than some tolerance. And I would have to give, a limit on the amount of tolerance I want to have. And that would be 0.5 times 10 raised to the power of the number of significant figures I want. And the number of significant figures I want is 6. And then I would have to obviously calculate my estimated relative error at the end of every iteration. And that would be the absolute value of my old guess minus the new guess divided by the new guess to get my estimated relative error. And so it would look something like this. And we have to start off this with it being larger than the tolerance. I could say tolerance plus 1 just so that the loop starts. And that's what I get. Except maybe it didn't work. What is x old? What is x new? What is my tolerance? My tolerance is huge. Oh, I didn't do negative number of sig figs. That's it. Now we go. So it requires a bunch of iterations. A lot of iterations to hit that tolerance. Not so good. Let me compare iterations for the bisection method versus iterations for Regula Falsi. For the bisection method, this is a nice review of bisection method. If I want it to be a tolerance of 0.5 times 10 to the negative 6 power, that would be 0.1, 2, 3, 4, 5, 6 zeros and then a 5. And then with the bisection method, another thing we can think about is since the 0 we're finding is 0, isn't it? Yeah, that's a problem. Do you see my problem? When do we care about relative error? And when do we care about absolute error? And to give you a reminder, my estimated relative error that I'm calculating each iteration is my previous iterate minus my current iterate divided by the current one. I'm running into an issue because this is what I'm using to tell if I'm close to convergence. I want that error to be small. What's the problem, though, with this problem? Yeah, dividing by 0 is a problem because the 0 that my algorithm is finding is located at x equals 0. And so when my algorithm actually does get close to having each iterate get close to the number 0, then suddenly this is like dividing by 0, and it's not really meaningful as a measure of how well I'm converging. This only works if the zero that I'm finding is something like the number 5 or 500, or even like, 1 out of a million, something that's not zero, as long as it's definitely a finite number that's non-zero, this works. But in our case, it doesn't work because we're converging towards 0. We don't want to divide by 0. So that was bad. What I should use instead is absolute relative error. And that means I just don't divide by the new iterate. So now let's try it. It's still a lot of iterations. Let me count the number of iterations. I'm going to start off with 0 iterations. Maybe we'll call it 1 iteration because I am calculating this thing before the loop starts. And then we'll print how many iterations it took. Took 37 iterations to get to 6 significant figures of accuracy. It took 37 iterations of Regula Falsi. Let's do the same thing with the bisection method. And the great thing about the bisection method is that we don't even have to run the program to know what it's going to do, because the interval always gets cut in half every time. So after 1 iteration of the bisection method, the width of my interval is 1, and each time I'm going to go up in 1 iteration, I'm going to cut this interval in half. So we just have to do this and find out when does it get smaller than 6 significant figures. When do I see that 7? Okay, so it would be 21 iterations with the bisection method. Okay, so this time bisection wins. Bisection wins because it took 37 iterations with Regula Falsi, 21 with bisection. What's even better about the bisection method? Starts with an F. F-L-O-P-S. The bisection method has way fewer flops because to calculate the midpoint, you just add them and then divide by 2, right? But if I want to calculate the midpoint using the Regula Falsi method, now I've got a lot more flops involved because I've got to call the function a few times, and who knows if that function requires a lot of flops to evaluate. And then I've got to calculate the slope thing, and then I've got to subtract and divide. So bisection method turns out to be a lot better in this case. All right, this is your intermission. Stand up, stretch, touch your toes. I see too many people falling asleep. If you need to stand up, if that helps you stay awake better, you can also stand up during class. That doesn't bother me at all. But one more method, and this is the last one we're going to learn, I swear. This is the last second to last one, sorry. This is the second to the last root finding method that we're going to talk about in this class. We are going to take the super quick, speedy strength of Newton's method and combine it with the ultra reliable, trustworthy convergence of the bisection method and kind of mash them together. And the goal is this. We start with an interval. We want the function to have opposite signs on opposite ends. On each iteration, we try to use the Newton's method formula. We hope, with our fingers crossed, that Newton's method will give us a new iterate inside the interval we started with. If that doesn't happen, if Newton's method shoots us somewhere outside of that starting interval, then we reject what Newton's method is trying to do. We get suspicious because we think that kind of looks like Newton's method is trying to diverge on us. And so we throw out what Newton's method has to say and instead we just calculate the midpoint like the bisection method would do it. So we always try to use Newton's first because Newton's is faster, but if it looks too suspicious because it goes outside of our interval, then we just choose the midpoint. And then regardless of how we choose our new iterate, we have to test to see whether the function value is positive or negative there. That tells us whether we should replace the lower bound or the upper bound. And then we start over with a smaller interval and a new iterate to calculate Newton's method with. Does that make sense? Okay, so it's like all the ads you see for like, what is it? Man, I have the memory of like a shrimp. I was watching an ad for like Reese's and Oreo, was it? It was like a mashup between like Reese's and Oreo. Okay, that is what I was thinking of. Yeah, it's like Reese's pretty good, Oreos are pretty good. I haven't tried yet the Reese's Oreo. I don't know if it's any good or not. But that's the idea behind the Newton bisection method. So let's try it with the sine function. We're going to use the interval a equals 1.5 and b equals 4.5. And we're also going to use the 4.5 as our initial iterate for the Newton's method formula 2. And I'm going to do this in Excel and not with a calculator in the interest of saving time. So let's keep track of our iteration number. We'll keep track of the lower bound and the upper bound and which one we're using for Newton's method. And then for Newton's method, we're going to need the function evaluated at that point and the derivative of the function evaluated at that point. And then the new iterate and the function evaluated there. My function is sine, so I'm going to take sine of 4.5. And then the derivative is cosine, so we take cosine of 4.5. The next iterate is going to be the previous iterate minus the function divided by its derivative. And then I take sine of that, and it's negative. There's another thing that I should also do, which I should take f of a and f of b. So you can see which one's positive and which one's negative. That's the first iteration. So now let me ask you, when I have this new iterate, should I use it to replace a or b? B. Does everyone understand why I'm replacing the B and not A? Kevin? No? Okay. This is my new iterate. When I evaluated my function at the new iterate, it was negative. And if my function is negative, I need to look for which one of these is negative. And since f of b is negative, I can replace the b. I look for the function values, and the one that matches my new iterate gets replaced. Negative matches negative, so I replace it. If my new iterate had a positive function value, I had to replace a. But this time, A stays the same. B is replaced by my new iterate because they both have negative function values. And then I'm going to copy everything else over like that. Oh, and I also have to say that this is that. Okay. My new iterate is 0.00087 and it has a positive function value. So should I use that to replace A or B? I already made a mistake. What's my mistake?
It's outside of the bounds.
Yeah. Thank you, Sage. Yeah. So if you remember, if you're paying attention, we're trying to use the Newton bisection method. And right now I'm just using Newton's method basically. But what I should have been checking for, is like, is my new iterate actually inside the bounds? And the answer, even from the first iteration, was no. This number that I got was not between 1.5 and 4.5. It was outside of that interval. And so what I should do instead is calculate the midpoint. And to get the midpoint, I do A plus B divided by 2. And the midpoint, I need its function value. It's positive, and so if it's positive, do I replace the A or the B here? A. Yep. Sorry about that. We were just going along happily reproducing Newton's method, but we don't need Newton's method. We need to do this hybrid Newton bisection method. So this time, on the first iteration, we actually chose the midpoint instead of the Newton method. This time, let's make sure all of our formulas are working properly. This is my new iterate. Newton's method is suggesting 3.142. Is that inside my interval? Yes. Then we're going to go with the Newton method this time. Does it replace A or B?
B.
No, it replaces B. Because the function value of B is negative and the function value of my new iterate is negative 2. So we replace B, A stays the same. I'm going to copy everything else. Try to double check. Make sure everything is working. And voila, we already have 6 good sig figs, 3.14159. So anyways, this case is one example where you've got one iteration, the very, very first iteration, where we had to use the bisection method to keep us from leaving this interval. And then after just requiring the bisection method one time, then 2 Newton iterations got us to 6 significant figures of accuracy. Okay, did that make sense? Okay. And I guess the next step is to do this in Python. So let's open up our Python. I'm going to start with my Regula Falsi and then make it a Newton bisection. And what function am I trying to solve now? Sine of x. And my interval is from 1.5 to 4.5. Okay, so it's the same problem we just solved, but this time in Python. I'm also going to need the derivative. And I'll just keep it x new. It's fine. All right, so now this time I need a test to figure out is the new iteration inside the right interval. So if x new is less than a or x new is greater than b, I'm going to calculate a midpoint instead. Otherwise, I already have the new one, so it's fine. Then that changes my interval. I don't need that. We are going to calculate absolute relative error. Oh, by the way, I kind of messed it up earlier. We're still doing estimated absolute error on the previous example, and I changed it to absolute relative error, which doesn't make any sense. But, you know. We're getting close. I don't like how it's new. Let me just call it x. It's throwing me off. I think this is going to work. Do you think this is going to work? I appreciate the confidence, but I was more looking for like, do you see any obvious errors? Right? Tell me what you think, not what you feel.
You asked that. You changed it to estimated relative error, but your two other instances of it is backwards still.
Yep. Thank you, Aaron. Very good. Anything else we see? I guess we can always try it and see what happens. This seems like it kind of works. I think it's still messed up. I don't think I wrote the code right. Do you see why I don't think so? I get really close to pi, 3.14, and then it goes away from pi, and then really close to pi, and then away from pi. I think something about this is wrong. So if x is outside of the interval, then do the midpoint. And that needs to be right before we change what the interval is, which is good. And then I fix the new interval. We calculate a new value for x. Oh, that's the wrong part. Do you see it? What should that be instead of a? No.
Oh.
It should be an x. Yeah. Okay. Now I feel better. Whew. 4 iterations. It didn't tell me what the first one was because it doesn't have a print there, but I could put a print in there. There you go. So the first iteration did the midpoint and got me a 3, and then the second, third, and fourth iterations were just Newton method. Okay. But it looks right. Seems to get the right answer. That's the idea. So we saw this on your test, this comparison table. We've done this a whole bunch of times, but it's good to do it again. What's good about the Regula-Falsi method is that, yes, it's guaranteed to converge. Does it require us to know the derivative? No. Does it require a starting interval? Yes. Is it fast? Not particularly. Sometimes it's faster than bisection, and sometimes it's slower than bisection. And bisection is considered to be a pretty slow method. So I think it's safe to say that this is not a fast method. The Newton bisection method, is it guaranteed to converge? Yes, because of the bisection part. Does it require us to know the derivative? Yes. Does it require a starting interval? Yes. Is it fast? Yes. Okay, so there's still pros and cons, even with these fancy methods. Exercise 10. Perhaps you like the idea of using a Newton bisection method or Regula-Falsi method because they're safe methods. The bisection method is also a safe method. It's guaranteed to converge. But suppose you cannot find an initial interval such that the function values have opposite sign. What could you do? Any ideas? Yeah, exactly. Just start off using a different method. Start using secant method, then switch to Regula-Falsi when we do discover two iterates, A and B, such that their function values have opposite sign. Or start using Newton's method then switch to Newton bisection whenever you do discover two iterates of the Newton's method, such that their function values have opposite sign. And then you always choose the two iterates from your sequence of iterates that you generated that are closest together, that have opposite sign. It starts you off with the smallest possible interval, but then you can switch to using a safe method. And so you might start with secant and then switch to Regula Falsi if you don't know what the derivative of your function is. That could be a good method. Or if you do know what the derivative of your function is, then you could start by using Newton and then switch to Newton bisection. So this is the last thing we can do today. We're going to implement the Newton to Newton bisection method in Python and then solve the following equation given the initial iterate x naught equals 10 with 6 significant figures. So the zero of this function is at x equals 1. How many iterations use the Newton method formula? How many iterations bisected the interval? How many used the midpoint? Would the calculation fail if we simply use Newton's method? So I guess let's start from our Newton bisection method Python code and then try to make it start off by just using the Newton method because we're not going to have an interval to start from. We're just going to start off by using the x equals 10, I think. And my function is arctangent of x minus 1. What is the derivative of arctangent of x minus 1? One over x squared plus 1. But it's not just x squared, it's going to be x minus 1 squared. Okay, so that's my derivative. And then I start off by doing a Newton method iteration, and then that sign thing's going to have to come later, I guess. Because, no, maybe not, because we're looking for something that has the opposite sign of this initial place we're starting from. Now there's a chance that just plain old Newton's method could do the trick without having to actually switch to a Newton bisection method, right? Like if it never finds a value of the function that goes negative, that could work. So we might say, while the estimated relative error is greater than the tolerance, then this which is just the Newton method. But also, while we're doing the Newton method, we need to test if f of x times sine is less than 0, then I want it to end the loop. And I think break is the right command for that. I'm not 100% sure. I'm not a good syntax rememberer. Okay, so now we need to set up the estimated relative error and the tolerance. And we get that loop going. I also need a way to know that, no, that's fine. I like it. I need a way to know what my interval is going to be. I think that's a good way to set up your interval, because we're already saving the previous value of x, and then this is going to be the next one. Like I said before, really the fancy way to do things would be to keep a whole list of all the iterates you've generated and then choose the smallest interval, but that's a lot more effort too, and I don't know if we have the class time for it. But we've at least set up an interval where it switches from positive to negative, in function value at least. And then we're going to have this one that does the Newton bisection part. That's already guaranteed. I don't need to do that. Okay. Do you see any issues with this? If I press play, is it going to work? Aaron, you see any problems?
Not how I would have done it.
It's not how you would have done it? Tell me. Enlighten me.
Using break statements, just the break statement. Yeah.
Oh, that's like a CS no-no?
I mean, because you can structure it in a way you don't have to use it.
Yeah.
But
So I could say something like this: while estimated error is greater than tolerance, and f of x times sine is greater than 0. Is that what you're talking about? Or is there a smarter way to do it?
Yeah, basically.
And that way I don't need this if statement.
Because then we'll just exit that. That's good.
And then I can... I'm just curious, because I'm not a CS person. What's the reason why people don't like using break statement?
It's generally harder to follow a break statement than it is to just go, this while loop is no longer valid, so then it moves on. Throwing break statements kind of creates more of a arrows flying everywhere situation.
Is it just harder for humans to understand the code?
Yeah.
Okay, so it doesn't have anything to do with how the computer executes it. Oh, okay, okay. Okay. So let's try it. There's a print statement. So it is using the bisection method quite a bit, because you see it's only printing to the terminal here, or whatever you want to call this, the console. It's only printing to the console when it finds the midpoint in line 26 here. And so every single one of these places is places where Newton's method was throwing an answer outside of the interval, and then it has to go back to the midpoint to kind of center it in again. And this is a pretty decent tolerance, right? It was 6 sig figs, so I wonder if the answer is really... Do you have a caps lock on? Yeah, that's the number 1. Okay, good. So that's super accurate, I guess. 1.0 is our answer. So, I guess it works. How many times do we use the bisection method, and how many times do we use the Newton method, I wonder? It's hard to say. But I think because of where we started on the arctangent function, where it's really, really flat, the very first thing that would have happened is it would have calculated a positive function value, and then it would have shot it way over and calculated a negative function value. So it would have started the Newton bisection method immediately for this particular case. But it's funny to me how many times it had to bisect before it could start using Newton's method. Okay, there we go. It used Newton's method 3 times. All of the others were bisections, and then it used Newton's method 3 times there. And so this is a good use case, right, for saying, okay, even if I don't know a starting interval, I can use Newton's method to find a starting interval. And then I'm going to use Newton bisection because I know Newton's faster and it's going to be more accurate, and it probably saved us a lot of bisection method steps there at the end. But I did need the bisection method to keep Newton from diverging away from the root.